Yeah, and thank you all for coming. I'm very excited and feel privileged to be here. So today I'll be giving my thesis defense talk titled Designing In-situ Interaction with Ubiquitous Robots. And so the field of robotics have been growing tremendously in the past few decades. Instead of being restricted to factories where only expert users were allowed to interact with robots, and even then behind glass walls, now robots are increasingly becoming parts of our daily lives, interacting with us in many different ways. We see an increase in number of robots as well as type of robots, ranging from humanoid robots in STEM education and shopping malls to non-humanoid robots in the form of vacuum robots and autonomous vehicles. And so we have seen similar trends in computing where computers were initially isolated and used only by experts. And as technology matured, we start to see that see the emergence of personal computers. And now we see that computers are everywhere and everyone interacts with many computing devices. And so we see this overall exponential growth in number of computing devices and decay in size. And so while robotic is in the exact same stage now, we believe that it'll follow a similar trend. We'll see an exponential growth in number of robots and decrease in size of the robots. And as size of robots decrease, their capacity to do meaningful work also decreases. And so one of the ways to overcome this is to use a large number of robots that can collectively achieve meaningful tasks. And so one technology that enables this is swarm robotics. Researchers in this field have looked at how to leverage large number of robots to accomplish meaningful tasks that otherwise would have been impossible alone. And so robots have been used in applications like search and rescue, where efficient and fast coverages of large areas are needed. They can also work together to manipulate heavy objects. They can also collectively navigate through uneven, complex terrains. And so these multi-robot systems have been deployed in specific locations like warehouses to efficiently sort packages. And so as we approach this era of ubiquitous robots, the interaction between the user and robots become more and more important. And so in this work, I propose this concept of ubiquitous robotic interfaces, or URIs, where we'll be seeing swarms of small robots. They'll be physically moving around and sense our environment. They'll also collectively manipulate objects around us, for us, and they will interact with us when it's necessary. And so researchers have studied mostly the functional components of URIs, such as sensing and manipulation. But a key question that still remains is, how do we interact with them? And so to study this, I first broke it down into two components. Specifically, I was interested in learning how should the robots display information to the users such that it's comprehensible, and how can you allow users to command large number of robots? So in terms of display or output from the robots, earlier works in HRI or human-robot interaction have explored designing output with humanoid robots. So in addition to verbal communications, researchers have looked at leveraging anthropomorphic features like facial expression, gaze, gesture, as well as posture. So while these features are useful for social interaction, many robots do not have these features and would require additional hardware, which can be costly. It can also mislead users into overestimating robot social skills. And its high resemblance to human can limit how easily these robots blend into our environment. So to address these issues, people have looked at one feature that is common across most, if not all, robots, their mobility. And so prior works from psychology, such as Heidel and Simmel's animation, have shown the immense expressive power that motion has. Just by having simple geometries move in a particular way, we are able to convey comprehensible information such as intent or affect of these simple geometries. And so recent works in HRI have leveraged exactly this to create more expressive non-humanoid robot. They use different motion features like trajectory or speed to successfully convey abstract information like intent or affect. In terms of command or input to the users, researchers have looked at different ways, and those include verbal, voice control, nonverbal through gesture or controllers, as well as programming, which is primarily used by experts. And so most of the prior work deals with one-on-one human-robot interaction. And when we scale this interaction to multi-robot systems, there are several challenges that arise, both in terms of input and output. First, multi-robot systems have significantly higher degrees of freedom than a single robot. And so to display meaningful information, a naive approach would involve applying findings from a single robot to each of the robots. However, that approach may not yield the same results, as prior work has shown that people's perception changes based on the number of robots. So it's necessary to find a more effective approach that truly leverages and take advantage of the high degree of freedom of a multi-robot system. In terms of input, it's also difficult to know what is the best way to enable users to effectively command such a large number of robots. Another challenge is that as these robots become ubiquitous, the robots need to have this ability to interact with anyone at any time. And so as we see, robots will become increasingly versatile, completing many tasks, but they'll still be around people. And so they need this ability to communicate and interact with people even during the task. And in terms of input, again, the robots will be around people, and so will be in public and personal spaces, so they need to be usable even by people who don't have prior experience interacting with a robot. And lastly, the robots need to adapt to how people interact. Research has shown that humans inherently interact with the world through different sensory channels. We communicate verbally and non-verbally through gesture and touch. So in order to provide this seamless interaction, robots will also need to display information through these channels, as well as understand multimodal input from the users. And so the goal of this thesis is to design this multimodal and ubiquitous interaction patterns with multi-robot systems. To achieve this, my approach has been to first develop and use interactive multi-robot platforms. Prior works in swarm robotics and multi-robot systems have mostly focused on developing hardware that is specifically designed to complete a task. And so it doesn't have the features necessary for real-time interaction, such as fast robots and ability to detect users' input. To address this, my colleagues and I built new interactive platforms and then designed multimodal interaction patterns that leverages these different sensory channels, as well as the high degree of freedom of a multi-robot system. And lastly, I included people in the process. So I either studied how humans perceive different stimuli that I designed, or co-design with the participants by having them generate the appropriate stimuli for different interactions. And so in this thesis, I look at both how to display information with multi-robot systems, primarily using motion, as it's one of the common features across most, if not all, robots, and how I investigated how to enable users to command large number of robots. In terms of display, I looked at how to leverage motion to visually convey information, especially when the robots are out of reach, as well as through touch when the robots are nearby users. For the visual display, I looked at how to embed expressiveness as well as intent into the swarm robot motion. And for touch, I looked at how people perceive different touch stimuli from the robots, as well as how people use robots to convey different touch messages. And lastly, I investigated how to enable users to command large number of robots. And because prior work has mostly focused on developing a functional mean that is not based on how users prefer to control a large number of robots. So to study these problems, I first built a multi-robot platform named Zoids, together with our previous postdoc, Mathieu Legat. Zoids is an open source platform that consists of multiple mobile robots controlled by a central computer. The size and form factor allows them to more easily blend into our environment and allow users to manipulate multiple robots simultaneously. And each of the robots consists of the following parts, and that allows them to localize, detect touch, move, and communicate with a central computer. It has the overall communication structure as shown here. First, the robots read this structured light pattern from a projector above to localize, and then sends that information to a central computer, which then sends back the desired states for each robot. And so in the first chapter, I will first talk about how to display information visually through motion. And so more specifically, the main research question is, how do we design expressive multi-robot motion? First, if we start with a simple single robot, we have 3 degrees of freedom. And so we can leverage this, we can leverage velocity and acceleration, or even its path to convey information. And so researchers have leveraged these features to successfully convey information like intent and affect. But what happens if you have many robots? You have n times the 3 degrees of freedom, and so how can you best leverage these additional degrees of freedom? From past literature, we observed mainly 2 ways, either through the use of icons or through abstract motion. For iconic display, researchers like Alonso Mora have looked at how to coordinate these robots spatially and temporally to deliver graphical representations of the content, similar to how screens use pixels. And while this is a valid method, in some cases it doesn't work, like when the robots are already doing other tasks like navigation or manipulation. On the other hand, abstract motion can be leveraged even while completing other tasks. The challenge with abstract motion is that we don't know how to best leverage, take advantage of, and parameterize these additional robots. You could have the robots move independently with different speeds and paths, but with so many robots, it's difficult to scale and understand what these motions intuitively mean. To address this scaling issue, we were inspired by swarms in nature. These organisms, like flocks of birds and schools of fish, are able to exhibit complex behaviors through simple distributed rules. And so while these animals use these behaviors as means for survival, I see an opportunity to use these behaviors to generate more expressive swarm robot motion. And so I first identified 5 different types of behaviors from prior literature, including the ones shown here. And in addition to behavior, prior works in single robot motion perception have shown that speed and smoothness have significant effects. And so I expected that these could also be used to generate expressive multi-robot motion. And so to address the main research question, I first hypothesized that swarm behaviors will have significant effect on human perception and thus can be leveraged to generate expressive swarm robot motion. Prior work has shown that number of robots, even just number of robots, affect human perception. I also expected, as I said before, that speed and smoothness will have significant effects similar to the prior work. So to study this, we performed a crowdsourced between subject experiment. The crowdsourced study allowed us to reach larger population more quickly and allowed us to use a between subject study design. And that allowed participants to only watch one motion instead of all of the motions. And that uses user fatigue as well as carryover context and sensitization effects. So before doing a video study, we looked at prior literature that compares results from live and video-based studies. So Woods et al. Have studied how people perceive robots when they approach them from different angles and found comparable results from both live and video-based studies. And so because our study is also purely visual, similar to their study, we concluded that video-based trial will be sufficient. So to run the online study, I filmed all the motions, and here are the videos of different swarm behaviors with the robots, including rendezvous, dispersion, random, torus, and flock. I also varied the speed to see its effect. I also changed smoothness, so it's either smooth or synchronously jittery or asynchronously jittery. And so overall, we had 3 independent variables that include swarm behaviors, speed, and smoothness. So after watching the video of different motion, participants were asked to rate their perception of the robots. We first measured urgency, as we envisioned that robots will be around us and will have to convey information with varying urgency. We also looked at more robot-specific perception, like animacy, likability, and perceived safety. And these measures allow us to design behaviors that are likable, safe, and has varying amount of animacy. User experience is also important for designing any interaction. And so I use this questionnaire to measure hedonic, pragmatic, and attractive qualities. And lastly, I measure participants' perceived emotion. because it can be an implicit indication of the state of the robots. It can be used to indicate how busy the robots are or how well they're solving a task. So after running the aligned study with 962 participants, we analyzed the results and highlight some of the statistically significant results here. In each box, the mean value and standard errors are shown. And the results show that, as I hypothesized, swarm behavior does significantly affect user perception in many categories, including some of which are shown here. So both rendezvous and dispersion were perceived quite similarly, but they were perceived differently from other swarm behaviors such as random, torus, and flock. And that suggests that, except for rendezvous and dispersion, others are perceived differently and can be used to convey different types of information. For speed and smoothness, they yielded similar results as prior work on single robot motion perception. So faster speed was perceived as more arousing, hedonic, animate, and urgent, whereas for smoothness, smoother motion was perceived as more hedonic and likable. And these, again, results again support our hypothesis. And so overall, all of these results can be used as guidelines for future robot designers when they're developing abstract swarm motion. So as an example, we demonstrate one of our own examples. So imagine your phone is on a desk and someone is calling you about an urgent matter. How should we design the swarm motion? So first, we will consider what perception we want to elicit. Since it's an urgent call, we want to alert the user in a pleasant manner. So we look at the relevant categories such as these. And first, for behavior, we can see that rendezvous and dispersion have this desired high arousal and urgency. However, as we want to draw users' attention toward a specific point, in this case, which is the phone, we chose the rendezvous behavior. If it was a non-urgent call, we could have used flocking behavior as it has lower induced arousal level. For speed, we chose faster speed due to its higher rating in arousal and urgency. And lastly, for smoothness, we chose a smoother motion as it is rated more likable than jittery motions. There are also interaction effects between speed and smoothness for arousal and willingness to attend. However, for both, fast and smooth motion was still the most arousing and had the highest rating for willingness to attend, so it works. So here's the resulting fast, smooth rendezvous motion. And so to summarize, in this first chapter, we looked at how to embed expressiveness into swarm robot motion. And as we hypothesized, swarm behavior, speed, and smoothness all had significant effects and thus could be leveraged to generate more expressive swarm robot motion. Similar to the previous chapter, here we also explore how to visually display information, in this case, the intent of the robots. So as we see increasing number of robots, it is important for the robots to accomplish tasks in a, not only in an efficient manner, but also in a legible manner to allow users to read and predict where the robots is going to do, preferably even before the execution. And so the main research question for this chapter is, how can you enable users to read and understand the intent of multi-robot systems? And so for a single robot, Dragon et al. Have introduced this concept of legible motion and how it's different fundamentally from a predictable motion. For a predictable motion, the main objective is get to the target as efficiently as possible. And so this usually leads to a straight path unless there's an obstacle in between. On the other hand, legible motion, the main objective is enable a observer to be able to understand where the robot is going to, preferably early on. And so this led to a curved path where it initially moves away from the non-target to indicate that that's not the target. And so you could apply the same concept to a multi-robot system where the robots follow this curved path. However, there are costs associated with path-based legible motion. Because for users who already know where the target is, there's a mismatch between the expected and legible path in the beginning, and thus that can create confusion. There's also an increase in trajectory length, and with more robots, that becomes even more significant. Fortunately, swarms of robots have other motion features that could be leveraged. Robots could use their shape could form into an arrow-like shape to point towards where the target is while following a straight path. They can also change the distribution or density within this overall shape to guide users' attention toward the goal, or they could leverage one of the swarm behaviors, rendezvous behavior, to all merge toward this target. And so out of these features, I was particularly interested in density and rendezvous behavior. Density is interesting because it is one of the pre-attentive processing features along with color and size. And these features can be detected very rapidly by human eyes and thus could be used to generate legible motion that can be quickly understood. On the other hand, swarm behavior, specifically rendezvous behavior, could be used to improve legibility by having many robots from different directions all merge toward the goal. So the research question for this chapter is, how do we leverage these features to generate legible motion, and how do they perform in comparison? So we first formulate the problem as follows. We have the robots on one side, shown by the blue circles, as well as row of possible targets on the other. And there are many parameters that determine how difficult the task is, such as the parameters shown here. And I determined the values experimentally through pilot studies to create a sufficiently challenging task. However, for one of the parameters, I decided to vary its value as I expected to have different effects based on the type of legible motion. In order to create a baseline for comparison, we generated the control condition where the robots move synchronously straight toward the goal. An optimization that minimizes the trajectory length is used to compute this trajectory. And that results in a motion something like this. To generate path-based legible motion, we use the same objectives from latest prior work on single robot legible motion. I won't have time to go into all the detail, but the resulting motion looks something like this, where it initially moves more quickly towards the target and then plateaus, but still maintains the formation. To generate density-based legible motion, I use findings from vision perception research. Specifically, I use the features that are considered pre-attentive, such as color. So there are features that are considered pre-attentive, such as color, density, and size. And here I use density because it doesn't require any external light sources or shape-changing capabilities. And so my approach has been to create this denser region within the overall shape and have that pointed towards the target. And so to implement this, I use an algorithm called centroidal voronoi tessellation, which has been used to fill a shape evenly. And so this has been used to generate evenly filled shapes with robots for animation purpose. So I use the same algorithm to fill these two regions with specified number of robots to generate this desired configuration. So after computing this desired configuration, each robot needs to be assigned to one of the positions in that configuration. And so I used the Hungarian algorithm to compute the optimal assignment. And finally, I also adjusted the speed of each of the robots to ensure, based on the distance, and to ensure that they'll reach this desired configuration early on while still moving towards the goal. And so the resulting motion is shown here. So the robots quickly move towards this desired configuration and then maintains it until the end. Lastly, I wanted to leverage swarm behavior, specifically the rendezvous behavior, to enhance legibility. For rendezvous behavior, the agents typically move towards the same point, but as these are real robots that can't be, where there can't be any overlap, I computed the configuration where the robots are packed as closely as possible using prior literature on circle packing. Then I used the same Hungarian algorithm to find the optimal assignments and then generated straight paths towards that assignment for each robot. And so the resulting motion is as shown here, where the center of the robot maintained the straight path, but then the robots all merge towards this target. So now that we have defined and designed these different types of legible motion, we want to compare their performance. So for the study, I had the following independent variables. So first, there were different legibility cues, including the control condition. We also varied the initial radius, as we expected to have different effects on legibility cues. And then finally, we also looked at target difficulty. And that's determined by how many targets are next to the goal. And so the 3 innermost targets are labeled as hard, as they have 2 other targets next to them, whereas the 2 outer ones are labeled as easy, as they only have 1 other targets. And we looked at this because for path-based legible motion, we expect this to have an effect, as the path-based legible motion has an algorithm that depends on the relative locations of the target. And so first, I made hypotheses on the effects of legibility cues. Specifically, I expected all legible motion to improve the legibility. For path-based one, it has been shown true for a single robot motion, and for the other 2 conditions, they have some sort of additional cue about where the target is, and so I expect it to improve legibility compared to the control condition. I also looked at, made hypotheses on target difficulty. As I said before, because path-based legible motion has algorithm that depends on the relative location of the targets, I expect it to suffer based on the target difficulty, whereas the other ones, it only depends on the absolute position of the target, and so it won't be affected by target difficulty. So for the study, we used a between subjects online study where 231 participants viewed a video online. So the task for the participants was to watch this video moving towards a target. And then their job was to stop the video when they were confident where the goal was. They then selected the target they thought the robots are going to by selecting one of the gray circles. For each trial, I measured the prediction time, prediction confidence, as well as accuracy. And using these measures, I computed an overall legibility score using a formula from prior work. I also asked them to rate the predictability and legibility of the motion. Yes?
Was there any incentive for them to actually be accurate and fast?
So I asked them to predict as soon as they think they have an answer. And so people will obviously have different standards for that, but we looked across different people, so yeah. So looking at the results for legibility cues, we saw that for both prediction confidence as well as self-reported legibility rating, only rendezvous behavior performed significantly better than the control condition, thus supporting only our 3rd hypothesis and not the others. And this is surprising, especially for path-based legible motion, as it has been shown to improve legibility for a single robot. This suggests that perhaps even just increasing the number of robots improve legibility, but further investigation will be needed to confirm this. For effects of target difficulty, we saw significant effects on prediction confidence, prediction accuracy, and overall legibility score. As expected, we saw a significant difference between the target difficulties for path-based legible motion. But we did not see any significant effect of target difficulty for density or rendezvous-based legible motion. And that supports all of our 3 hypotheses. One additional interesting trend was that path-based legible motion had the highest overall legibility score when the target was easy. And so this suggests that perhaps an ideal legible motion would be composed of, would use path-based legible motion when the target is easy, but then use rendezvous-based motion for harder targets. And so the goal of chapter 2 was to visually convey intent of the robots using the motion. And the results show that rendezvous behavior performed the best. However, there are other trends that suggest that perhaps a best solution would be composed of a mixture of these different legibility cues based on the context of the task. And so the 2 previous chapters were focused on leveraging motion to visually display information. This chapter will look at how to leverage motion to use touch from a swarm of robots. So touch is an integral part of our daily lives. It allows us to not only discriminate shapes and textures, but also is embedded in our social interactions and affective communication. And so to integrate touch and human-robot interaction, researchers have studied haptic interaction with a single humanoid or zoomorphic robot. For instance, it has been shown that humans touching a robot can have positive effects, such as improving the mood and stimulating social interaction among elderly. Fewer works have explored robots touching humans. It has been shown to have positive impact on the amount of effort people put on tasks and perceive unfairness. And so while people have looked at haptic interaction with a single humanoid or zoomorphic robot, none have looked at haptic interaction with a swarm of non-humanoid robots. And as I introduced in the introduction, we envision that swarms of robots will be ubiquitous and accomplishing meaningful tasks like sensing and manipulation. And then when it's necessary, they will approach us to provide direct haptic notifications that can be tailored to convey different messages. We also see a good opportunity to use these robots as a medium for remote social touch, enabling people in distant places to connect through touch. So for this work, we focus on the touch or haptic display with swarm robots. So first, to better understand what could be done with this type of system, we first began by exploring its design space. We then studied how humans perceive different touch stimuli from the robots. And we dove deeper into the remote social touch application and ran a study to derive this user-defined interactions for social touch. So we first looked at the design space of haptic stimuli with the robots. And so with a single robot, you could provide forces of different types, either normal or shear, by translating and rotating the robot. We can vary the frequency at which we apply these forces, either high or low, as well as the amplitudes of the forces. And as the robot is mobile, you can also change where the robot provides the haptic feedback. It can be your finger, your palm, or your forearm. And it can also be any other part that is on a flat surface, but research has shown that arm is the most socially acceptable body part to touch. And so in this work, we primarily focus on haptic display on user's forearm. With a swarm of robots, one of the simplest things you can change is number of robots. It can be one to few to many robots. You can also change how they're spatially distributed. It can be on one side or both sides of the arm to provide the squeeze sensation. You can also change the temporal coordination among the robots. It can be synchronous or sequential to provide this stroke-like sensation. You can also coordinate the forces of the robots. It can be homogeneous or heterogeneous.
Yes. Is the human passive during all of these interactions?
Yes, for this one, the human is passive. It's just receiving all the... Yeah, so another interesting design space is their visible motion. So as the robots have to produce haptic sensations, have to move to produce haptic sensations, there's inherently this visible motion that accompanies the haptic stimuli. And so, for instance, when the robots are providing this wave-like haptic stimuli, you also see this motion, wave-like motion. And so this visual aspect is unique to our system, as other haptic devices are either usually worn or held by the user. And so you can't see it at all. And so with this type of haptic stimuli, one question we had was, how do people perceive touch from swarm robots? To get a better sense, we ran a perception study where participants received different haptic stimuli and then self-reported their perception. And so out of the parameters that we discussed earlier, we first chose to look at a subset of them due to time constraint. In particular, we decided to study the lower level parameters like force parameters as well as number of robots. As there are no other work that look at effect of haptic display with swarm robots, we formed our hypothesis based on prior work in swarm robot motion perception and haptics. And so similar to prior work in swarm robot motion perception, we expect increasing number of robots will increase arousal, urgency, and valence. And similar to work in haptics, we expect higher force amplitudes to be less pleasant and higher frequency forces to be more arousing and urgent. And so to measure human perception of the robots, we use similar metrics as in chapter 1, and so I won't go into detail here. So we had the setup as above, where robots provide haptic patterns to the user's forearm. So for the trial, the robots will align themselves, move forward, making contact with the user's forearm, and then provide 3 repetitions of the haptic stimuli and then move back. The users will then fill out a set of questionnaire on an iPad. So for the results, for number of robots, we found the following results. As we hypothesized, increasing the number of robots increased arousal and urgency, but not the valence. It actually decreased the perceived valence. And this suggests that while seeing more robots is pleasant, having more robots touch you is less pleasant. So similar to prior works in haptics, we saw that higher force amplitudes were less pleasant and that higher frequency forces were more arousing and urgent. So the main takeaway is that there's a trade-off when you increase the number of robots for touch interactions, in that it increases the urgency and arousal, but comes at the cost of likability and perceived safety. So lastly, we dove deeper into the remote social touch application. And the first question we had is, how should the robots convey social touch? With swarming robots, you have many degrees of freedom, so it's unclear how to best coordinate these robots. To best capture this, we asked the users themselves to generate appropriate behaviors for different social touch. So we first generated this set of reference for our elicitation by looking at prior work. And Jones et al. Have identified different categories for meanings of touch, as shown here. And we also wanted to convey basic set of emotions, so we took Ekman's 6 emotions. So given the reference shown before, we asked the participants to use the above setup to generate the appropriate interaction that best conveys the message. They used a multi-touchscreen to control up to 4 robots, which they could test on themselves before deciding on the most representative interaction. And so from previous study, we found that force amplitude plays a significant role. And so for this study, we used a bigger robot that's capable of outputting larger amount of forces. Okay, so here's some of the example interactions that the participants came up with. Given the reference shown on the left participants brainstorm and then tested different interactions before selecting the most representative ones, some of which are shown here. So one of the interesting trend was that people use visual effects of the motion as well as the context location to deliver this contextual information that's hard to convey, especially for abstract social touch. And so to convey surprise emotion, participants use this dispersed motion to where the robots move away from the forearm. To convey afraid emotion, participants had a robot hide in the corner of the user's arm. And so the main takeaways for this study is that the visual aspect as well as the context location is important, especially to provide this contextual information that's hard to convey through touch alone. And so in chapter 3, I looked at how to leverage touch from the robots. The 2 studies I ran showed that it's important to consider the number of robots that touch users, as well as how and where the robots move to provide these haptic stimuli. So in the last 3 chapters, I talked about how the robots should convey information to the users. In the last one, I will switch gears and talk about how to enable users to command large number of robots. For a single robot, researchers have developed many different ways to control it. And that include verbal, nonverbal, and written through coding, which is primarily used by experts. However, with a large number of robots, it becomes a much more challenging task, especially for non-expert users who are not used to interacting with robots. There have been some attempts to address this. Researchers have tried using EMG and IMU sensors to detect muscle signals of the user's forearm to derive this set of hand gestures for controlling multi-robot systems. People also have used computer vision to detect gesture and body posture and derive this set of controlled gestures. And while these provide a means to control multi-robot systems, they don't take into account users' preference, and rather it only focuses on what the sensors can detect and differentiate. And so instead of the previous bottom-up approach, where the sensors are chosen first, and then they choose this set of gestures that this sensor can distinguish, I flip this around and use a top-down approach by first focusing on how the users prefer to command large number of robots. And so prior works in HCI and HRI have taken similar approach to generate user-defined gestures for different applications like surface computing and human-drone interaction. In our case, the main research question is, how do users prefer to command a large number of robots? How is it different from the expert-defined or sensor-based command set, and what modality do people use for different commands? We also looked at the effect of number of robots, as prior work has shown that people's perception change based on the number of robots, and work in psychology have shown that individual behavior changes based on the presence of others. And lastly, we also wanted to look at the effect of proximity to the robots. Prior work on HRI have shown that human perception changes based on proximity. And so to test this question, we had several independent variables, including number of robots, where it varied from 1, 5 to 20. We also tested 2 different proximity zones, either intimate or personal. And we also compiled this list of different commands for multi-robot systems from prior work. And it can be categorized to robot selection, inter-robot interaction, user-robot interaction, and robot environment interaction. To run the study, we had the following setup with a TV monitor showing the pictorial prompt, and the robots were placed on a table with users standing next to it. And so the procedure was as followed. First, we showed the participants this pictorial flashcard containing the initial and final state of the robots. We then asked them to perform whatever action they think is necessary to command the robots to go from the initial to the final state. We told them there were no constraints, and we told them that there were no constraints. After each trial, we asked the participants to recall and explain their actions to get a better understanding of what they did and why they did it. So first, looking at the first research question, we compiled a user-defined interaction set by combining responses from the users. Some of the examples are shown here. So to command a robot to move to a specific location, people pointed, and for a larger number of robots, they just grabbed one instead of controlling all of them. And so combining all of the user's command, we generate this user-defined command set. I won't have time to go into details about all of this, but you can check with me later. So here's the breakdown of the modality for all of the user-generated interaction. And so we found that gesture is the most common modality, and that supports the prior work that mostly leveraged gesture for multi-robot systems. However, there's still significant numbers of touch and verbal interactions, and so the control set is multimodal, but with an emphasis on gesture. We also saw an interesting trend where verbal commands were almost always accompanied by gesture. So even for participants whose primary modality was verbal.
So as a single unit move towards me, start.
And you can see that he uses gesture on the side of his body. And when I asked him afterwards, he said he didn't notice that he was using it, but he just subconsciously used it to complement the verbal command. The second question was about effect of number of robots, and we indeed see this effect. And so even for similar tasks, people use varying number of hands or fingers based on the number of robots. And so we saw this effect for both gesture and touch interaction. For gesture, we saw that with the increase of number of robots, we saw increase in two-handed gestures and decrease in use of one or two fingers. And similar trend was also observed in touch interaction. And one participant, there were other participants as well, but one participant noted that I often wanted to use both hands when interacting with a group of robots, even though I already knew that a single hand would work the same. And so because there was no constraint, they could use whatever number of robots, but they still felt compelled to use more hands. We also saw an effect on how people control many robots through touch. With more robots, instead of trying to directly touch all of the robots like here, participants were more likely to use a different approach where they only control a subset of the robots and expected the others to follow. Or some only used one of the robots and expected the rest to follow as well. So for touch interaction, we saw this shift in control paradigm as number of robots is increased. Instead of trying to control all of the robots, people only touched subset of the robots and expected the others to follow. And last question was about effect of proximity. We also observed significant effects for proximity. Specifically, we saw that proximity affected how many hands people use. When the robots were further away, people tended to use more one-handed gesture. While we didn't investigate the exact reason behind this, we suspect that it had to do with the fact that people tended to lean in when the robots were further away, and so it's more difficult to use two-handed gestures when they're leaning, and so they relied on one-handed gesture more. And so to summarize, the goal of this chapter was to investigate how to enable users to command large number of robots. We ran a study and found that people use multimodal inputs with emphasis on gesture, and that number of robots as well as proximity affects how people command. And so that implies that an ideal system interface will require this robot state-dependent vocabulary to accommodate users. And so in summary, the goal of this thesis was to answer the following question: how do we interact with multi-robot systems? I broke it down into two components: display via motion and command, and looked at how to generate multimodal output from the robots using the motion of the robots, and how to understand multimodal input from the users. Here I summarize the findings from each chapter. For first chapter, we found that swarm behavior, speed, and smoothness, they all can be leveraged to generate more expressive motion. And to convey intent, swarm behavior has been found to be the most effective, but perhaps an ideal one will use a mixture of different legibility cues. For haptic display with robots, we saw that number of robots is very important, and also the visual aspect of the motion as well as contact location is important. And lastly, to command large number of robots, people use multimodal input, and number of robots as well as proximity affects how people command large number of robots. And so while I investigated several aspects of human multi-robot interaction, there's still many more pieces that could be explored in the future, one of which is context. Most of the studies I ran didn't have specific context or a setting. And so, and that was done on purpose to generate more generalizable results. However, when designing interaction with real robots at real application, it will be necessary to confirm whether these results hold or if different interaction is needed. Another aspect that could be useful to explore in the future is size. This current thesis uses small robots, Zoids, that are inherently safe. It has many benefits, but if we change the size drastically, we can expect the interaction experience will also drastically change. For instance, when you have larger robots, the perceived safety will be a much more important criteria for an interaction. And as we see emergence of robots like autonomous vehicles and delivery robots, this aspect of size is important to explore. And so Mark Weiser once famously said, the most profound technologies are those that disappear. And swarms of centimeter scale robots have this ability to literally disappear into the background, but then also come out into our foreground when it's needed. And so I plan on continuing to study this ubiquitous interaction with multi-robot systems, and also how to leverage these robots as programmable physical tools that can help people achieve their goals in a way that has been possible before. And so in conclusion, the robots will become ubiquitous on our streets and home. Robots will be physically moving around, sensing our environment, manipulating objects, but then also interact with us visually and through touch. And so with this thesis, I hope to have made some progress towards enabling this future of ubiquitous robots. We're almost at the end, and I just wanted to take a short amount of time to thank everyone who's been involved in this one way or the other. I want to thank my advisor, Sean Fulmer, for being an inspiration figure throughout this journey and making this possible. Due to time, I'll be short with this. I know you took a little longer. And I thank all the committee members for being here, for introducing me to the field of haptics, HCI, HRI, and making this whole thesis possible. I also want to thank all my collaborators for making all of these works possible. It would have been impossible without everyone's help, especially Mathieu Legac for building the robots together with me. I want to thank past and current Shapies. They were instrumental in running and designing and doing research. We also have very unique lab traditions like TTL, which stands for Traditional Tuesday Lunch, where everyone used to cook. Not anymore, but we have a different thing going on. I also want to thank my fiance, Jen, plus Boba, which is the famous dog on Instagram, as well as mom, dad, and my brother, Fred. I also want to thank my friends and different support groups, including especially Friday night tennis group. It's been great. And I also want to thank my funding sources, Samson Scholarship and Hasso Plattner Institute. So thank you all for coming and listening, and I'll take any questions. Yes.
Thank you for the great presentation. It seems like a lot of work. It seems like the design of the shape of the robot was key to your studies. Is there a reason why you chose a cylinder instead of a ball or a cube, etc.?
I guess, yeah. Compared to a cube, I think it was more straightforward in terms of design and trying to make the robot as small as possible to use a cylinder shape. Comparing with a cube, there are literature on perception of different shapes, and people usually tend to perceive rounder shapes more positively. And so instead of cube, we actually had a cube-shaped robot, but didn't end up using it, both because the perception as well as when you touch it, cubes have these pointing more edges that is not so conducive to touch. So we use this cylinder round shape. Yes.
In your last study, the last chapter, did you look at, or can you talk more about the kind of connection that there is between the modality that people were using, gesture, touch, or whatever, with the distance? Because it looks like the table was so big that if they want to, they couldn't reach
actually
the table.
Interesting. Yeah, that's a great question. I didn't see any significant interaction with the data, but what I observed was that, and that's because people who use touch mostly kind of stuck with touch. So it didn't matter whether the robots were far or close. And I think there was one video showing one of the participants like reaching out and using their hand to do it. And so a lot of the people like stuck with the modality that they used initially. And so surprisingly, I didn't see the effect of proximity. I think if the robots were even further away, then they would probably give up trying to use touch. But then for our case, I guess it was still reachable if you lean in. And so we didn't see that effect here. Yes.
How much did it cost to construct each individual robot?
Yeah, so right now we made about like 200 of the robots. So that came out to a cost of around $50 per robot. But I think if you do mass manufacturing, you could probably make that even lower. But for now, we spend around $50.
Per robot.
Per robot, yeah, not for the entire, yeah.
Is there a way to explore the non-minimum phase behavior of some of the devices, like standing robots or even drones, where you basically, in order to move forward, you have to back up a little bit because I just came from a conference where we had these standing robots, and you don't know whether they move or they stand or they just displays. But if they moved a little bit, maybe first away from me, and then I feel safe, and then it can interact with me.
I think, yeah, that's a great question. I think, so unfortunately, the studies I ran didn't really explore that aspect. It's mostly one directional for now. I am planning on looking more into this bidirectional interaction because I think that's definitely more important in the future where, you're not only gonna be receiving or sending. And so I think this, yeah, as you said, this interaction aspect is much more important. I think, yeah.
Easy to modify them to to implement that non-minimum phase or
Yes.
the opposite direction movement.
Yes.
Thank
I
you.
think that's very important, and yeah, but it's harder to design it because you have this bidirectional aspect of it. So yeah. Okay. Thank you all for coming. It was a pleasure, and happy Friday.